Okay, so let's start. So, welcome everyone to the live session for week 2 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur. I am Anant Singhal, a teaching assistant for the same, and I'll be assisting you in solving some of the similar assignment problems that have been given to you in your week 2 assignments. So in the last week, let's move ahead. So in the last week, we have already covered about the very basics of the modeling, like what is modeling, why it is required, uh, because we want to save a lot of resources even before the fabrication part. So that is why what we require compact modeling, and modeling is nothing but just some mathematical representation of the physics or the behavior of the device that we have. And we already covered some of the very basics that why are we even into the device scaling because we want to save a lot of resources and other things. And why are we calling it now nanoelectronics instead of micro? Because we are moving towards the sub nano regime of the semiconductors. Then covered or we ended our lecture with the topic of crystal structure, and we also covered some of the problems that are related to Miller indices. So as you can see in this week, we have some more similar topics which are again very basic. So initially, we'll be discussing the concept regarding the same. So we'll be doing the reciprocal space, that is nothing but the reciprocal, that means the Fourier transform of the direct space that we have. Then we'll see what do we mean by doping and how does band structure come into the picture, and also a term which is called as effective mass. So these are the things that we'll be going to cover in this particular lecture. So let me summarize again. So as I said in the last week, what we did is we studied about the crystal lattice. By lattice, what do we mean? We mean that we had a periodic arrangement of the atoms that we have. So we studied about FCC, BCC, and the third one was diamond cubic. So it was nothing but the silicon structure. So this is what silicon uses. So these were all the topics that were related to the direct lattice. By direct lattice, what do we mean? Let's say we have a cube and we have atoms. Let's say for FCC, we know that we have atoms at all the corners, and then we have atoms at all the faces. So let me make it one here and one here. So this is what we studied about the direct lattice. So if we do if we do a Fourier transform of the direct lattice, that is from time domain to the frequency domain, this is what we call as reciprocal lattice. So we'll be covering some of the problems that are related to reciprocal lattice that will easily clear your concepts. So maybe yeah, we can see some of the problems that will be more easier to understand. So the first problem, it says what is the ratio of the FCC primitive unit cell to the volume of the BCC unit primitive cell. So we have been given assume that the lattice constant A for both, oh, so for both BCC and ACC, the lattice constant is already given to you, which it says it is A. So this is actually a simpler problem. And then we need to calculate about the primitive. So one term here is primitive, and this is okay. So this is a direct problem, not a reciprocal lattice problem. So we'll be covering the reciprocal lattice problem in maybe the second problem. So first of all, we need to be aware that there are, what do we mean by primitive cell? So a primitive cell is nothing but number of atoms in a primitive cell is always one. This is what we need to know beforehand, is always one. So once we say that we have a primitive cell, the number of the atoms that can be there in a primitive cell are always one. Now we need to calculate the ratio between the FCC and the BCC. So let's first see about the FCC. So we know that for FCC, we have covered in the last lecture that the number of atoms per unit cell. So for FCC, the number of atoms per unit cell, we discussed that we have atoms at all the corners, that is a contribution of 1/8, and we have atoms at all the faces, and the contribution is half, and the faces are 6. So yeah, so this is 1 plus 3, that is 4 atoms are for the FCC, and for BCC, we also discussed sorry, for BCC, the number of atoms would be atoms at all the corners, and then we have a atom at the center, so it will be nothing but 2. So this is what we already discussed in the last class, that we have for FCC the number of atoms per unit cell is this. For BCC the number of unit cells, oh sorry, the number of atoms per unit cell is this. Now the question has been asking about the volume of the ratio of volume of primitive cell. So VFCC, I'm denoting it with VFCC, by the volume of BCC primitive. So it is asking for primitive, not for the per unit cell, but primitive. So this is what has been asked in the question. So first of all, so let me write the volume of primitive cell. So for, let's say, for FCC, now we know that in a single primitive cell the number of atoms can only be 1, so it will be a cube by, since FCC has a total of 4 atoms, so it should be a cube by 4. Since the primitive cell can only contain 1 atom, so it will be a cube by 4. Similarly, the volume of primitive cell for BCC would be, because BCC in total have 2 complete atoms, so it will be a cube by 2. So that we can say that in a primitive cell we have only single atom. So now the question is asking actually about the ratio of these two. So let's do that. I mean, this is a very straightforward problem now. So if I do primitive, then it would be a cube by 4 divided by a cube by 2. So we need to see if the question is asking, yeah, it is FCC by BCC. And the lattice constant, we already know that it is 1, so it should come out to be 1 by 2, which is the answer to this problem, and the correct answer would be option A. Is this clear? Is there any doubt? Okay, so maybe if not, then we can move ahead to the actual problem of the reciprocal lattice. So now the next problem says, what is the volume of the primitive cell? Primitive, again it is asking for primitive, so we need to be aware about the keywords. So one is primitive, then it is saying for the reciprocal now, and for FCC. And the lattice constant is also given as 5 nanometer. So we have a lot of information that is given in the problem itself. So yeah, if I say we have just calculated for the direct lattice that the volume of primitive cell for FCC. Okay, so we know that A is 5 nanometer. We just calculated it is nothing but what was that? A cube by 4, right? But this was for the direct lattice. So even if you try to calculate the volume of the direct lattice, let me show you the way how we do that so that you can calculate for anything. So volume is always given by, so let's say we are talking about FCC for now. So FCC, what do we have is, oh sorry, yeah, let me redraw this. Yeah, so let's say what do we have is, we have atoms at all the corners. Let me again redraw this. Okay, sorry. Yeah, so let's say we have atoms at all the corners, we know that. So let's just focus on a single atom and see what are the closest atoms. So let's say I'm focusing on this. So one closest atom would be this, one would be this, one would be, also we, what do we have? We also have a face centered. So let's say I'm making this because this will make more sense. So let's say what I'm calling this now, let's say this is x axis, this is let's say y axis, the vertical one, and inside one is the z-axis. So what we need to calculate? We need to calculate the closest distance. So one will be this, one will be this, and one will be this. So let's say I'm naming them something as A1. Let's say this is A2 and this is A3. So what I can say is because we know that volume in general in vector space is nothing but a dot product of one divided multiplied by the cross product of the remaining two. So first, what we need to calculate? We need to calculate the A1, A2, and A3. So we are initially doing it for the primitive, sorry, for the direct lattice space. Then we'll do the same for the reciprocal. So yeah, if I try to do that, it will be so A1. A1 is nothing but it is in the, if you see, it is in the YZ plane, right? Because this is the plane that it is in. Let me highlight that. So yeah, if I see this face, this is where the A1 vector is. So we have x as 0, right? So yz will be there, and you know that the distance between the closest distance would be, let me try to explain this also. So we know that this is A, right? The total width is A, so the half of that would be A by 2. So if I talk about, let's say the first vector, so this will be A by 2 for y and A by 2 for z because it's in the YZ plane. Then what do we have? What do we have? Next is A2. A2 is this vector. Now A2 is actually in, where is A2 is in? A2 is in XZ plane, right? So XZ plane is this, the bottom one. So there is no y in that. So A2 will be nothing but A by 2x plus A by 2z. Similarly, A3 is now in X and then Y plane, right? The front face that I'm talking about. So it will be nothing but A by 2y plus A by 2. Sorry, it is not in Y, but it's in X and Z. Oh no, it is in X and Y. Yeah, plus A by 2y. So now we just need to do the dot product and cross product. So if I try to calculate the volume, so it will be A by 2 if I take common. So from A1 it will be y plus z. Then the dot product by the cross product. So we know that how to do the cross product. It's nothing but writing the matrix. So for A2 it was x and z. So this will be A by 2, 0, A by 2. And it is A by 2, A by 2 and 0. So we already know how to calculate this. This is just basic mathematics. So for x cap, what do we have? We have x cap, for x cap we have minus a square by 4. Then we have minus y cap, which is again minus a square by 4. Then we have z cap, which is again which is a square by 4 positive. So let me try to explain how I did that. So for x, we uh, we do not take these two columns, and then we do the multiplication like this. So I just multiplied this minus this. So this is what minus a square by 4 is. Similarly, I did for y and z. And yeah, so now if I try to calculate, this should be a by 2y plus z. So if I take a square by 4 common from this, it should be minus x minus, sorry, this will be plus y and plus z. Now what do we need to do? We need to do the dot product of these two, right? So yeah, let's do that. So we know that any perpendicular dot product is 0, right? So y will only be done by y and z will be only be done by z. So if I take all the scalar quantities out, so this will be a cube by 8. So for y it is 1 plus z it is 1 again. So this is how we have come into a cube by 4. That is what we calculated there also, right? So this is one another way, and that this is actually a volume of direct lattice. Now to convert it into the reciprocal lattice, right? So reciprocal lattice, we know we only do the Fourier transform. So that will be nothing but 2 pi by the volume. So let's try to do that. So if I try to do the reciprocal now, So for reciprocal, we have certain formulas that are already well defined. So for reciprocal, we have the lattice vector which is b1, b2, b3. So let me write that. So b1 is given by 2 pi by volume. So volume is nothing but the direct lattice volume, which is this, multiplied by a2 cross a3. b2 is defined by 2 pi by volume a3 cross a1. Sorry, this is a1. And similarly, b3 is defined by 2 pi by volume. So since we have 3, so it will be a1 cross a2. And again, the final volume would be what? The same formula will be used. So the volume will be b1 dot b2 cross b3. So you can also try to calculate the volume side by side uh, in your notebooks, and I'm also doing the same simultaneously. So for b1, as I said, it is nothing but 2 pi by volume. So volume is a cube by 4. And then what do we have? A2 cross a3, right? Yeah. So A2 cross A3, I think we already calculated, which is this. So let me use that. A square by 4 minus x plus 5 plus z. So this would be A square by 4 minus x plus y plus z. This would be A and this 4 will be cancelled. So this would be 2 pi by A minus x plus y plus z. So this is how we calculate B1. Now we can do the same for B2 and B3. So let's do that quickly. So let's first calculate B2. So it will be 2 pi by volume, which is again this, and then it will be A3 cross A1, right? So let me write that A3 cross A1. So yeah, if we try to calculate A3 cross A1 now, which will be A3 and A1 we have already defined. So this is X, Y, Z. A3 will have the Z component as 0. So this will be A by 2, A by 2, 0. 1 will have the first component. So this will be the thing. So yeah, if I try to write B2 now, this will be 2 pi a cube by 4 x, we have a square by 4. So this is x cap. Y we have minus y cap, and for z we have plus z cap. So if I have done it correctly, so this should be again 4 will get cancelled. So b2 will come out to be 2 pi by a x minus y plus z. Okay, yeah. Similarly, if you do for b3, so b1 was this, x was minus, b2 by y was minus. Now b3, it will come out to be 2 pi by a x plus y minus z. So these are the three b1, b2, b3 we have calculated. Now we just need to calculate the volume, right? So yeah, let's do that quickly. So now we can say that the volume of the reciprocal lattice is nothing but b1 dot b2 cross b3. So yeah, b1 we calculated as 2 pi by a, 2 pi by a, then what do we have? Just give me a second, yeah. So it was 2 pi by a, b1 was minus x plus y plus z. And then we need to do the dot, okay, so we need to do the b2 and b3 cross product. So let's write that again. So all of that I'll take 2 pi by a common because we have it in common, so it will be square. So for b2 it was minus y, for b3 it was minus z. So this thing would become 2 pi by a cube minus x plus y plus z, and then this will become x should be 1 minus 1, so 0. Y would be minus y, so it will be plus 2y, and for z it would be plus 2z. We need to see, so and the dot product of these two. So I need to see if I have done it correctly. So y plus y will be 2 plus 2, so 2 pi by a whole cube, and this will be 4. So 2 cube is 8, and then 32 pi cube by a cube. So this is the volume of reciprocal lattice for FCC. So similarly, we can do the same calculation for BCC and all of those things. So let me write the shortcut. So for volume of reciprocal lattice for BCC, it is nothing but 16 pi cube by a cube. And for FCC, this is 32 pi cube by a cube. Now in the question, we already have the value of a, which is 5 nanometer, and the answer is in centimeters. So 5 nanometer is nothing but 5 10 raised power minus 7 centimeter. So we'll just need to put that here. Let's do that too. So volume of reciprocal lattice for FCC is 32 times pi cube, so 3.1417 something cube divided by a, which is 5 raised to minus 7 whole cube. So it should be multiplied by 21 because this will be 21, and this would be per centimeter cube. So we need to see what the answer will come like. So it should be around 32 into pi square is 10. We have 125. 525 should come out to be approximately 7 something, and this for 21 per centimeter cube. Is there a single option or there are multiple? Yeah, so 7.94. Yeah. Oh, so this should be plus 21. They have written it wrong. The correct answer to this problem is option A. So is this clear? Are you all able to understand how we have calculated the volume of reciprocal lattice and the direct lattice? Is there any doubt? Okay, so if not, then please let me know the answer to this quickly. So it says calculate the volume of, again we need to see the keywords, primitive, reciprocal, and it is asking for BCC and A is given. Quickly type your answers in the chat box, then we can move ahead. Okay, so for this, actually they have given the value of A, but the answer is in the form of like not the numerical value but A. So I have already given the formula. So the volume for reciprocal lattice for BCC is given by nothing but 16 pi cube by A cube, which is option C. So you can do the same calculations like we did for the FCC, and you will get to know that sorry, the volume of the reciprocal lattice for BCC direct lattice is nothing but 16 pi cube by AQ. So you can check this, I mean, after the class also, or you can check this in the lectures given by Professor Vivek Dixit. So now for further, what do we have? So this is how we have covered the concept of reciprocal lattice. So now we'll see some of the concepts that are related to doping, band structure, and effective mass. So actually, I mean, if I say in continuation, so the we need to understand how the band structure comes into the picture, and then the doping part. So let me try to explain you what is how this band or the energy of bands come into the picture. So this is nothing but very basic stuff from a class plus one, plus two. So you might have already studied about the chemical bonds, right? So we have few different type of chemical bonds. So what do we have? I mean, if I try to classify very broadly, we have primary and secondary. Secondary is very less forces, that means they are intermolecular or they are van der Waal forces. I mean, this is not is what relevant to us, because in all the semiconductor we'll be discussing about the strong bonds that are the primary bonds. So these are also can be classified into mainly the interatomic bonds. And if I try to classify that, they follow the electrostatic, they are electrostatic. And the second thing is they are pretty strong stable. Now you might have heard about, I mean, you might have heard the bond classification into these three. So all of these are primary. The first one is ionic, the second one is covalent, and the third one is metallic, right? So these are the three main classifications that we have. So ionic, I mean, there is a very well-known example, that is, let's say we have Na plus, in which we have a deficiency of an electron. We have a chlorine minus, in which we have an extra electron. So this electron will go here, and this will form a ionic bond and make NaCl for us. Then for covalent bond, let's say we have, again, covalent is nothing but sharing of electrons. So let's say we have a hydrogen atom which is only having a single atom, and when we have one more hydrogen atom, so this is interatomic. So these two will get shared, and this will be nothing but HH, or this is what we write as H2. So sharing of bonds is nothing but the covalent bonds. And for metallic, I mean, metallic are already there. So the most relevant bonds for the semiconductor physics are the covalent bonds. So these are the bonds around which the semiconductor physics will evolve, or revolve, I mean, not evolve. So let's try to go into deep how are these bond formation happening, and as a topic suggests, how are the bands coming into the picture. So for that we need to know about a theory which is called as the molecular orbital theory. So let's consider example of hydrogen bond only, because it is easy, because we have a single atom. So let's say we have hydrogen atom. So we have hydrogen atom. This is a nucleus which is positively charged. This is one atom which is 1s1, which is at the valence electron. This is what we say. This is nucleus. This is now 1s1. So now there are two things. One is the attraction of this positively charged nucleus to this electron. This is because this is positive, this is negative. And one is the repulsion of these two nucleus, right? Positive, positive will repel, and positive, negative will attract. So there are two types, two different type of criteria. So let's say we have this 1s, this as 1s. So one is when they are coming closer, there is some energy which is attractive. So this is what we call as the bonding orbital, which is what we denote as sigma 1s. And similarly, we have one more orbital which is due to the repulsion. So once they face repulsion, so they are coming closer, but they are feeling the repulsion. So this is what we call as anti-bonding orbital. So this is how we denote it, and this is what we say sigma star 1s. So now, as I said, there are two different types of bonding happening. One is due to the attraction and one is due to the repulsion. So what happens is, let's say we have one atom of this hydrogen here, one atom of this hydrogen here, and as they are coming closer to each other, so you might have seen this in your class plus one, plus two. So as they're coming here, they are splitting into two different energy levels. One is due to the attraction and one is due to the repulsion. So this is nothing but the anti-bonding and this is nothing but the bonding. So as per the molecular orbital theory, it is nothing but the number of atoms or the number of electrons in the bonding orbital should always be greater than that of the anti-bonding. So this both will get into the picture and this is empty. And this is how you see the band is forming. So we have two different bands of atom just for a single atom. So as I said, so what I am trying to say here is, let's say if I try to plot the energy with respect to the interatomic space, so there is up to a certain extent there would be a single atom that are coming to closer, but as we come close, there will be a lot of atoms. Oh, sorry, there will be a lot of bands. So let's say if we have a lot of atoms, because in hydrogen we are only talking about a single atom, so we have two levels only. So let's say for silicon we have four valence electrons in a space that are actually can have eight electrons. So we have a lot of band formations. So this is what molecular orbital theory is, and this is how the energy bands come into the picture. So since we'll be discussing a lot about silicon, so let's try to understand the MOT about the silicon only. So yeah, so let me write the topic of formation of energy bands, and we'll be discussing about silicon because that is the main source. So silicon, we know that the orbital is 1s2, 2s2, 2p6. So this is completely filled, and then the 3s1 is 3s2, 3p2. So in this, there can be actual 8 states, but only 4 are filled, right? So this should be the valence orbital first of all, or valence band. That is what we say in general. So now 2n electrons are there for the p that are present, but it can have 6 n states, right? So 3p6 can be the states. So there can be 6 states and only 2n states are filled. And we know that in the total of the valence band, that is the final, we have 2n plus 6n. So this will come from the 3s, this will come from the 3p. So there are total 8n states, out of which only 4n are filled, right? Is there any doubt in this? You can write in the chat box if you have any doubt, or if you don't have, you can just clarify that if you do not have any doubt. Is it clear till here? Okay, great. So let me try to explain now it in the form of again the an interatomic space, that is how they are coming closer with respect to the energy. So as I said, what do we have? We have 3s2. Let's say we have 3p2, right? So as they are coming closer, as I said, there will be a split of the different energies. One will be this bonding and one will be anti-bonding. So once we have this anti-bonding, so what do we have? So we have splitting of bonding orbitals, and then we have, so actual the structure is something like this. I'm just slightly trying to make. So as we have come till here, so this is actually, so you see the broadening is not as much, and here the broadening we have a certain band gap or the difference between the uh, molecular orbit, sorry, the valence and the conduction band. So if you try to see here now, so let's say at this line only, if you try to see, so let's say this is one point, this is the second point, now this is the third point, and this is the fourth point. So you see there could be n number of splittings here. And similarly, after we cross the band gap, there would be n number of splittings here. So this space is what we call as the valence band. This space is actually what we call as the conduction band. And the difference between the valence band and the conduction band is what we call as the band gap. So I mean, in a textbook, what you see is you see a diagram something like this, in which they say this is EC, this is EV, and this is EG. So that's it. That is only just a very easy representation of the same. In reality, the energy band diagrams are not flat as it is, as you can see in this particular picture. So energy band diagrams are having some curvature, but uh, due to I mean, just to explain it in very simple words, what do they do is they just make the topmost line of the valence band as the valence energy valence band, and the bottommost line of the conduction band as the conduction band energy, and the difference between that would be the energy band gap. So this is how the band formation happens. And once we move even ahead, when the broadening would be very high, so this would be ionic, this would be covalent, that is what we are doing. And when there is no broadening happened, this is nothing but metallic. So we'll be dealing with a covalent space only, which is this line exactly. And this is from where it is coming from, the energy band gap, which is this. Yeah. So yeah, if we try to see now, so I mean, let's see. So we have brought three classification. You might have heard about that. One is insulator, one is semiconductors, and the third one is conductors. So we can easily classify them now in terms of now the energy band gap. So once we have an energy band gap which is very high, let's say it is greater than 3.5 electron volt. So this is what we say are the insulators, because we need a lot of energy that is more than 3.5 electron volt to jump the electron from the valence band to the conduction band. So for semiconductors, what do we have? We have a band gap of approximately 1 electron volt. And for conductor, there is no band gap, right? So there is overlap of valence band and conduction band. So they are readily conducting. And in semiconductor, they can be partially conducting or they can be partially insulating also. So yeah, I mean, this is what I wanted to classify. So let's say if I try to make a periodic table. So generally 3 to 5 elements are semiconductor elements. So we know this is carbon, silicon, then germanium. Third may we have boron, aluminium, then gallium, then NPAS. So this is the category where we are playing with mostly the insulators. And then, I mean, even if I talk more broader, then we have, I think we have, I'm not sure about the table if I'm making it correctly, but we have hydrogen, helium, lithium, beryllium, yeah, something like this, Na, magnesium, I think. So these are all metals which are highly conducting. Then we have one more, which is six, seven, eight. We don't see because those are completely inert, but yeah, let's see six. Sorry, this should be oxygen, sulfur, maybe silurium. Then we have fluorine, chlorine, bromine. So these are all insulators. And at last we also have this noble gases, which is hydrogen. Then we have helium, lithium, I think neon or something something like that. So these are completely inert gases. So the topic or the interest of this course would be more or less nothing but this particular block only. So this is what we are calling as these semiconductors, which are mostly from 3 to 5 semiconductors. You might have heard this term a lot uh, while you study that 3 to 5 elements are mostly the semiconductors. Is there any doubt in this basic understanding of semiconductors? how this bond formation or the bands are coming into the picture. Great. Yeah. Now, if it is clear, then I mean, most of the things are clear now. So, actually, now the semiconductor are classified into two broad categories. So, we started with the classification of material, which are kind of insulator, kind of semiconductor or conductors. Now, we are actually classifying the semiconductor. So, it can be classified into different things. So, the most common classification is intrinsic and extrinsic. So, do you have any idea what is our intrinsic semiconductor? Any idea? Just a guess? Yeah. So, as you said, it is pure. Pure, by pure we mean it is does not have any impurity. So let's say a basic example of silicon only. We have seen that it has four valence electrons, right? So similarly, let's say we have a lot of silicon. We are having silicon, and this is like a chain. So this will be shared by this. Let's say I'm making a long term. This will be shared by this. This will be shared by this, and this will be shared by this. And this is how the chain is happening. So now you see that the valence band of this silicon. Let's say if I try to make again the same thing. So let's say this is the conduction band, this is the valence band. You see the valence band is completely filled. And the conduction band, we need certain energy. So let's say I'm talking about at 0 Kelvin as of now, there is no energy that is associated. So we have a completely filled valence band and we have a completely empty conduction band, right? So can we say that this is how is it acting? Because these electrons are not free because it is completely filled, so the electrons cannot move. And if the electron cannot move from valence to conduction band, what type of semiconductors they are? Sorry, what kind of materials they are? So it will act like a pure insulator, right? Because we don't have any energy to have this electron getting transferred from conduction band to valence band. Because once this get transferred, there will be some movement here also, and this since this is empty, so this will be a free electron, right? But for now, we don't have any energy. So what we see is at 0 Kelvin, that is at no application of any voltage or thermal energy, intrinsic semiconductors acts as pure insulators. Now, if I talk about the same at 300 Kelvin, let's say at room temperature, so there will be some thermal energy, right? So now, if I try to make the band diagram again, so let's say we have these filled electrons now. So this is valence band, this is conduction band. So now I have given some thermal energy, and somehow this electron has gone from the valence band to the conduction band. So let's say I'm denoting this as red. So this electron has come here, and now what it has done? It has created a deficiency of electron here, right? So due to this thermal energy, what do we have? We have a free electron now, right? Free electron means we have some current, right? So it is now conducting. And so this is what we are calling as free electron, and this deficiency that it has created, it this is what we call as hole. So hole is actually not a particle, but the deficiency that has been created by the electron that has gone from the valence band to the conduction band is what we call as hole. And just to give it some physical quantification, what we do is we give the same effective mass, uh, but just with a positive charge to the hole. And since they are pure, So what do we have is the number of electron concentration should always be equals to the number of hole concentration, and it should be equals to the intrinsic concentration. So this is the property of any intrinsic semiconductor. That same amount of hole and electron should be there, then only it will be purely neutral, right? Is it clear? The intrinsic semiconductor? Okay. Then the second thing that we have is the extrinsic one. So as the previous one, it was the pure semiconductor, that is we have don't have any impurity. So now the main term that we have is deliberately. So what we are doing is we are doing it intentionally. We are adding some impurity in the semiconductor. So deliberately adding the impurity. So do you know what is this process called as? Yeah, this is what we call as doping, which is your second topic of this particular week. So by doping the semiconductor or by deliberately adding the impurity to any semiconductor is what we are called as the extrinsic semiconductor, and they are not pure, they are impure or impure, whatever they, I think impure is the word. So why are we doing that or how we are doing that? Let's see that. So we can have now extrinsic into classification to two types. One is N type and one is P type. So let's just take as I said that 3 to 5 group are also come from the semiconductor. So let's take example of N type first. So let's say I'm taking a phosphorus atom, which is group 5. That means it has 5 electrons, right? 5 valence electrons. Let me make it here, and we have replaced that with silicon. So this electron will be shared by this electron will be shared by this electron will be shared by this, and let's say this electron will be shared by this. So now we have an additional 3 electron, right? So this is how we have made it conducting just by adding some impurity. So we have one extra electron, and similarly for P type, we have boron, for example, which only has 3. So it actually has a deficiency. So I mean, if I may do the same thing again, this will be shared by this will be shared by this. Now there is no sharing of this. So there is a deficiency of this electron, and hence what we are calling this as P type. So there is a deficiency, that is a hole is created. So this is the basic classification of N type and P type, and all of these semiconductor follow a law called as mass action law. So I'm currently talking about equilibrium. I'm not applying any voltage or anything. So the mass of action law states that, I mean, if you remember, this was the condition that the number of electrons and holes should be equal, that is equal to the intrinsic concentration for the intrinsic semiconductors. But for extrinsic, what do we have? The multiplication for the the concentration of electron and hole should be always equals to Ni square. So this is the mass action law that we have. That is let's say if we try to increase this, so it will decrease by default. But the multiplication should always be equal to the Ni square, because that is what the equilibrium says. So this only holds at equilibrium. This is the main condition. Is this clear till now? Is there any doubt? Yeah, okay. So let's move ahead then. If this clear, so let's try to do this problem now. This is actually related to the mass action law. So maybe you can take 2 minutes and let me know what is the answer. So it is a single silicon crystal which is doped with some arsenic ions, atoms. What is the equilibrium hole concentration it is asking? So it is at equilibrium, so we can apply the mass action law, and the intrinsic concentration is also given. So maybe you can take 2-3 minutes and type your answers in the chat box. Okay, so let me also try to solve the same. So we have a silicon crystal which is doped with arsenic. Arsenic means it is group 5, right? So this should be a anti-semiconductor now. So we know that the at equilibrium mass action laws hold. So NP should be equals to Ni square. So N is actually given, which is 10 to the power 15. And I is also given, which is, so all of them are in per centimeter cube only. So this should be 1.5 square, that is 2.25 divided by 10 to the 20. So P will be coming out to be 2.25. So this should be into 10 raised by 5. Yeah, so option C is the correct answer. That is correct. So this is how we calculate. So similarly, we have one more question. Try to do the same also. So it has a silicon crystal which is doped with Nd. So for your reference, Nd is donor concentration. That means it is N type. And Na is acceptor concentration. That means it is P type. So if Nd is greater than Na, then it is a N type impurity. If Na is greater than Nd, it is a P type semiconductor. Not impurity, sorry, it is semiconductor. So we have Nd given the intrinsic carrier concentration, what could be the electron and hole concentration assuming complete impurity ionization. So we have Nd doping, right? So we need to calculate the minority carrier concentration. That is, what could be the electron and hole concentration. Since we have doping as Nd, so the minority would be holes only. So try to do it using the mass action law again, because again we are talking about equilibrium only. We are not applying any voltage. And type your answer in the chat box, or maybe you can open your mic and tell. That is not a problem. You can take few minutes. Okay, so yeah, so let's see. So we have ND, so we have an anti-semiconductor, so N would be again directly times per 13, and NP is Ni square. So the whole concentration would be 10 is per 20 divided by 10 is per 13, which is 10 is per 7 per centimeter cube. Yeah, so option B is correct. That is true. So yeah, now again we'll check the understanding based upon the doping. So this problem says we have a bar of gallium arsenide, which is doped with silicon such that the silicon atoms occupy gallium and arsenide sites. So which one of the following statement is true? So try to think. So let me give you some hints. So gallium, we know it is P type because it is group 3, right? Then arsenic, we know it is N type because it is group 5. So what could be the true statement in all of those four? You can try, you can have a try, maybe take few minutes, and then I'll also try to explain the same. Yeah, sure. So let's try that. So we have, so let's say we try to make a structure only. So we have the silicon. We know we have the silicon. So let's say gallium and arsenide. So gallium we have three, right? So one it requires one, and arsenic it is actually five. So to fulfill this, what we can do is silicon can give its electron to this. So silicon can act as a n-type dopant, right? So this electron can act as a n-type dopant for the gallium. So silicon can act as a n-type dopant in case of arsenic. So there are two options that are so either sorry n-type. Let me clarify this. Oh, for gallium it says gallium, yeah. So n-type for gallium is this and this. So either A can be correct or D can be correct. B and C cannot be correct because silicon is giving its electron to this. So silicon can act as a n-type dopant to gallium. And for arsenic, what is the case? Arsenic already have an extra atom. So once silicon gives this atom to this hole will be actually compensated by this. So silicon can have a p-type dopant for the arsenic. Is it clear? Does it make sense? Okay, sure. So as you see that gallium we are deprived of one electron. So this silicon, if we try to give this electron to this will be having another hole created by this, right? Now this hole we can compensate by using an extra electron from arsenic because arsenic already have five. So oh, I can see it. You cannot you cannot see the cursor, right? This is what you're saying? Yeah, but you can see the screen, right? Oh, so now you can see it's changing now. This yellow thing. Yeah, it could be. It could be. So you can try maybe rejoining. I can wait for a minute. No problem. Can you see the screen now? And this red also, right? Yeah. So what I was trying to say is this gallium is deprived of one electron, right? Because it is group three. So we can take one electron from silicon and give it to this. And once we do it, this will create a hole at silicon, right? And arsenic already have an extra electron, so we can use this to fill this. Is this clear? So if it is clear, then what are you saying that silicon is acting like a n-type dopant to gallium and p-type dopant to arsenic? Yeah. So the correct answer is option A. So silicon atom acts as p-type dopant to arsenic and n-type dopant to gallium. Okay, so now I think we can move ahead. So this is again a similar problem using the mass action law. So it says we are doped with this much donor atoms and it is additionally doped with this much acceptor also. So yeah, this is actually a good problem. Try to do it and let me know the answers quickly. What is the equilibrium electron concentration it is asking. So again the hint would be if Nd is greater than N, if N is greater than Nd. So this is N-type semiconductor, this is P-type. And Nd means N and A means P. So quickly take maybe 1 or 2 minutes and then try to give the answer. Okay, so let me also try to do it side by side. So ND we have 10 per 15 per centimeter cube. Na we have 5 times 10 per 17 per centimeter cube. So it is what kind of a semiconductor? Yeah, because Na is greater than Nd. So if it is a p-type semiconductor, so we can directly write the value of p would be this, right? And N we can calculate using the mass action law because N is a minority carriers. So it would be Ni is given. Yeah, it's given 2.25 times 10 to the 20 divided by 5 times 10 to the 17. This is 32250. This should come out to be 450 per centimeter cube, which is option A. So the clever part here was it was given ND, so we can somehow get confused and we can say that this is the value of N. But in reality, it is not because we have a p-type doping. Is it clear? Okay. So now what we have covered almost everything, I think. Let me see. Yeah. So we have covered the reciprocal space, we have covered the doping part, and we have also seen how the band structure. So the topic that is left is effective mass. So let me also cover this then. So for effective mass, we need to understand what is a EK diagram. Let me try to explain that. So it is nothing but a energy versus momentum diagram, EK diagram. You might have heard in the lectures also. And we'll study the concept of effective mass here. So we know that energy, let's say for any electron would be nothing but half mv square. So let's say we are taking a electron. So I'm writing this as mn star, which is some mass, which I'm calling it as effective mass, and it is nothing but velocity square. This is a very basic formula, and the momentum is given by mv, right? So I can write this as, if I come out to be mv, so I can write this as p square, and there would be some one more m. Is this clear till now? I mean, this is the basic formulas that we study. Yeah. And we know that the momentum is also given by h cross times k, which is the wave number. So if I just try to put it here, so I'll get E is p square by 2 mn star, right? So if I put it here, so I'll get this as h square by 2 mn star times k square, right? So this is all constant, let's say. So we can clearly see that energy is related to k square, right? Which is nothing but a parabola, right? Let's say if we have energy here, this is energy here and momentum here, or wave number which is proportional to momentum only. So we'll have some parabola kind of characteristics. So this is what we call as the EK diagram. So now you can clearly see that higher the effective mass, lesser will be the slope, right? By slope, I mean the differentiation. So let's do that too. So if I try to do the differentiation with respect to x-axis, let's say d by dk, this would be nothing but h square by mn times k. And if I do the double differentiation, it would be h square by mn. Is it clear what I've done here? Okay, so I can easily write now the effective mass as h square by this thing, the slope. So now you can clearly see if this number is higher, this will be lower. So lesser the effective mass, higher would be the slope. So what I'm trying to say, so let's say this is one thing, and the second thing is this. This is more flatter parabola. So this is less slope. This means this is higher mass. And the blue one is, it is high slope and less mass. This is higher slope and less mass. Let's say I'm writing M for now. Is this concept clear? So that is why we say that, yeah, is there any doubt? Oh, so this is the slope term, right? So what I'm saying is if we have this term as high, the mn, because the denominator is high, this mn will be lower, right? So the slope you can see it is higher there. Like this is more sharp. If you differentiate this, this will be more sharper, and this will be more constant, the red one. Yeah. So as we have a higher slope, will have a lesser mass. That is what I've written. And opposite of this is this. Yeah. So if we even apply some more basic concepts, we know that according to Newton's second law, F is nothing but ma, and A we know that it is nothing but dV by dt. So why I'm doing it is because I want to give you some clarity regarding the velocity also. And we know that the force is nothing, it is nothing but charge into electric field also. So I can easily write this as dV by dt as, okay, not this. It should be QE by Mn star. And we have just calculated this. So let's say there is some velocity. If I try to integrate it, let's say which is what I call as Vd. So I'll explain this later in the third lecture, I mean the third week, which this term is called as drift velocity in very detail. And let's say the collision time is tau for now. So this will be nothing but Vd will come out to be QE by Mn star times tau. And yeah, so I can write this something as Q tau by Mn star times E. So I've written E separately because you might have seen this Vd equals to mu E somewhere in your books. So I'm just trying to relate the mobility with respect to the mass. So higher the mass, lesser will be the mobility, right? I mean, it can be analogous to humans also. If we have very high weight, it is difficult for us to move. So similarly, because electron have a lesser effective mass, then that is why the mobility of the electrons are higher. Is it clear? Yeah. So this is one basic concept that I wanted to clear. So this is what we call as the effective mass. So higher the mass, lower will be the mobility, or lower the mass, faster the electron can move. We have also covered the EK diagram now. So this is a question related to that only. So it says in the EK diagram, select all that are true. So if the actual EK diagram, once we make it, it can be direct, indirect. So let me make it direct only. So this is actually the conduction band. This is the valence band. So this is how a EK diagram looks like. This is K and this is energy. So it says each portion of the curve represents the allowed band of energy. So yeah, so this is actually all the allowed band of energies. So option A is correct. Then the second option says the curves have zero slope at the bottom, top and bottom. So you see here and here. Can we say it is zero slope? At these rand points, can you say it is zero slope? Yeah. Why? Because we have a local minimum, right? The differentiation needs to be zero. Otherwise, the transition won't happen. This is a local maxima. So this is also correct. Then the curves are parabolic in nature. That is also correct. Near the valence and the conduction band both are parabolic. The curves are parabolic near the bottom of the conduction. Yeah. So all of these. So answer would be ABCD. So this is just a question just to give you more clarity regarding the EK diagram. So this is our direct band gap semiconductor. We also have indirect band gap semiconductors in which we have change in momentum also. So we have plots like this at different k values, but different momentum. So for now, I mean, it is fine. We can have a detailed discussion later for this particular topic because it is quite detailed. So is this clear? So we have also kind of covered the concept of effective mass. Let me see if we have further problems. Otherwise, we can dismiss the lecture. So we have one more problem actually, which is this, which is for a particle in 1D infinite potential. The wave function is this. So has it already been covered in the lecture? Can you confirm? This particular problem, I mean the concept of Schrodinger equation, solution of Schrodinger equation for an infinite well. Oh, okay, okay, no problem. I think it will be covered in the next lecture also. Let me see the topics. Okay, wait. Yeah. So it is density of states. Yeah, Fermi direct needs to become from. Okay, so I think we can do this particular problem in the next lecture. That is not a problem. So is there any doubt in these four topics that we are having? Yeah, sure. So as I've given, I think did you attend the last week lecture? Okay, so let me, yeah. So this is my mail ID. If you have any doubt, you can mail me anytime. This is singhal.6 idj.ac.in. And yeah, so there is this YouTube channel also. So if you search my name on YouTube, so I upload this lectures regularly, the recordings. You can type Anant Singhal NPTEL, it will come. So I'll upload this lecture also like in half an hour from now, and you can check if you have any doubts in that too. Yeah. So yeah, I think we can dismiss the class for today, and we'll meet the same time next week. So yeah, thank you for joining.